Okay. When we left off in chapter 25, I had done the example of, I believe it was a concave mirror, and I had been demonstrating the use of these sign conventions. So what I want to do, so the one we had done, was this one, okay? Where an object was outside the focal point and we were generating a real image. What I want to do now is the example of, so this is still a concave mirror. Again, I want to show you how things change depending on where we put the object. In this case, instead of the object being outside the focal length, we're going to put the object inside the focal length, okay? And we're going to try to calculate where this image is forming. So, the data, okay, so I think last time our focal length was 15 centimeters, we'll keep it at that, okay? And then I'm going to give an object distance of 10 centimeters and an object height of also 10 centimeters, right? So again, these distances, object distance, the location of the object compared to the vertex or where the principal optical axis meets the mirror. And then our image distance is going to be measured from that same point to wherever the image forms. And focal length is given, so the master mirror equation gives the relationship between focal length, object distance, and image distance. So I can go ahead and rearrange that to solve for my image distance. I did this last time, I'm just going to do it quickly here. All right, so when we go and look at the sign conventions, what are we going to put in? Let's start with focal length, right? Notice positive if the focal point's on the front side of the mirror. What's the front side of a mirror? How do we define that? Hmm? The shiny side, right? This is the side you're supposed to be looking in, the side that's coated, side that's doing all the bouncing, right? So if the focal point, in other words, if the mirror curves, right, in that concave sort of way, we're going to give it a positive focal length. If it did the opposite, convex, we give it negative. Object's always going to be on the front of a mirror. It doesn't really make sense for it to be anywhere else. And then image, notice image distance is positive if the image is on the front, and negative if the image is on the back. So, what have we got here? Here's the focal point. Here's the shiny side of the mirror. And so our focal point is on the front side of this mirror. So I'm going to go ahead and call and just make sure that I put in, when I put in these numbers, it's going to be 1 over a positive 15 centimeters, minus 1 over, and then my object distance always positive, that's 1 over 10. And I put that all in my calculator and make sure I get the -1, the inverting everything, and I end up with negative 30 centimeters for my image distance. Okay, so we stop and we take a look. All right, what does the negative sign mean according to our conventions? This image is forming on the back side of the mirror. Is that consistent with our picture here? Yes, remember this picture isn't made up. It's determined by the physics of what's happening with the 3 principal rays doing the ray tracing and the geometry of optics. And so as we can see here, right, our 3 principal rays are doing what they're doing, but no image is forming on the front side of this mirror, it's forming on the back side of this mirror, which means it's what kind of image? It has to be a virtual image. There's no way around it. The only way that images forming on the backside of a mirror exist is in your head. So, and that's what our negative sign here is trying to tell us, right? It's forming on the back, and so because it's a mirror, we know it has to be a virtual image forming on the back side. And if we go and calculate the magnification here, then my magnification's negative image distance over object distance, which is going to be negative a negative 30 all over an object distance of 10. And what's a negative 30 over 10? Positive 3, isn't it? So what does the sign convention tell us about positive magnification? What do we know about the image if the magnification is positive? It's upright. So this is a virtual, upright, magnified image. That factor of 3 right there, okay? It tells me that this thing is 3 times bigger. So that if I wanted to go find the height of the image, right? The height of the image is equal to the ratio height of the image to height of the object is equal to the magnification. So that means the height of the image is 3 times the height of the object. If the height of the object is 10, this means that my image is 30 centimeters tall. And this example does a much better job than the first one I did at showing you, right, that the physics of the ray tracing and what we get out in terms of our sign conventions and our mathematics is consistent. So just again, I'm not going to expect you to be able to reproduce a ray traced diagram. I'm not asking you to do any ray tracing. But having the diagram there, right, as a way to check your math, right? It's the visualization and more or less is provided for you because all of these pictures are in the textbook, and I'm also taking you through all of these pictures. All right, let's do an example now of what happens when we use a convex mirror, right? This is where the shiny side bows outward. So what side is the focal point in for this? So front side is over here, the side that the object is on, shiny side of the mirror right here, okay? So what side is the focal point on, front or back? It's on the back, right? So look at your sign conventions. What are we going to need to make sure to do? Negative focal length. This is where you are going to have the most frustration. Oftentimes students report to me that they don't have any trouble like seeing where the focal point is or even doing the calculation. What will mess you up, and why Wiley Plus will say that you're wrong over and over again, is you'll forget a minus sign like on a focal length or an image distance or something like that, right? So just be mindful of your signs at all times. All right, so I'm just using 15 centimeter focal length. There's a historical reason for that, and it's mostly because a 15 centimeter focal length, when I did ray tracing on the board, is easy to see. I should probably go in and update all my numbers. We'll do an object height of 10 centimeters, and we're going to do an object distance of 20 centimeters away from this thing, right? So right here, we're saying this is 20 centimeters, and we're going to solve for the image distance. Now, can we predict the sign on this image distance just based from the ray tracing diagram? What's it going to be? It's going to be negative, isn't it? We're getting a virtual image. So we know that it's going to form on the back side of the mirror. Okay, so the ray tracing diagram tells me it's going to be virtual. Looks like the ray tracing diagram is also predicting an upright. So what do we expect the magnification to turn out to be? Positive. And I'm seeing reduced, right, in this ray tracing diagram, which needs to be shorter than the object height. So let's see if that all comes out. We already know how that's solved for this. Now, of course, in your homework, you'll probably be asked to give it an image distance and asked to solve for, the homework is always harder, isn't it? They're always trying to throw curveballs at you and stuff like that. But I wanted to make sure that we grounded all of this as a exercise in keeping your signs correct. Everything else is simply a question of what they're asking you to solve for doing math. All right, so let's see. This is 1 over, and I'm going to say negative 15. And where did that negative sign come from? focal length is negative because this is a convex mirror. The focal point is on the back side, so we gotta put a negative 15 on there. Minus 1 over, and I got a 20 centimeter, that's positive 20 because it's always positive. And then, oops, this is image distance, okay? When I calculated that out, I got negative 8.57 centimeters. Okay, so we pause. Are we good? Like, do we need a negative sign on our image distance? Yes, we do, right? Because it's on the back side, so that's good. The magnification, negative image distance over object distance, that's a negative of a negative 8.57, all divided by 20. When I did that, I got 0.43. Okay, so what is a positive 0.43? Tell me about the image. It's reduced, isn't it? 0.4 is less than 1, so this is smaller, and it's upright because of that positive magnification. Mind your signs, right? Use the diagrams as a way to orient yourself, visualize what's going on in the problem, and make sure that they're in relative agreement. And you should be all right. Okay, that was the end of chapter 25. I do want to get started on chapter 26. I want to cover a few things. So chapter 25, we spent all of our time learning about reflection. It was the law of reflection. Chapter 26 is all about refraction. And then when we get to chapter 27, it's going to be all about diffraction and interference. So this is a big chapter because there's a lot of topics we're covering. But as you're going to see tomorrow, we've already done all of the math. Because the equations end up being almost the same. There's a couple things I'll teach you today, and then tomorrow we'll get into ray tracing of lenses and things. So what is refraction? Refraction is the bending of light rays because the medium changed. So in this example right here, is that pencil really bent? No, pencils don't do this normally, right? Okay. What's going on here is light, upon entering or exiting the water, has shifted the direction of travel. And the only way that a wave will shift its direction of travel is if its speed changes. And the only way that a wave can change its speed is to change what? The speed of a wave depends on the medium in which it's traveling. So this bending of the pencil, or if you've ever sat on the edge of a pool, dangling your legs in the pool and your legs look all funny and short or whatever, right? You're talking to somebody who's in the pool treading water and they look all squished, okay? You are seeing refraction. You are seeing the bending of light as it exits the water and comes to your eyes. Now your brain insists on the fact that light travels in straight lines. And so what we're seeing here is a virtual image of that pencil under the water. It's virtual because the only way that pencil can bend is in our brains. Okay? And again, the insistence of our brains in making light go in straight lines.
When a beam of light strikes the surface of a transparent material, the beam is both refracted and reflected at the surface. This is the reflected beam, and this is the refracted beam. Notice how the angle of each beam changes as the block is rotated.
Okay, so there's refraction taking place in a plastic block. So we've got to tackle several things here, okay? We've got to tackle what's going on with the speed of light in materials. And then we need to tackle how we calculate what that beam of light's going to do as it enters and exits materials. So let's take a look at these pictures and I'll lay out what's going on here, okay? And let's talk first about how light changes its speed. We calculated in class, or at least I told you, right, that the speed of light was equal to this thing that Maxwell found out, the 1 over the square root of mu naught times epsilon naught. And mu naught and epsilon naught are all about magnetic fields and electric fields. That naught on them, okay, means that these are the values for the strength of electricity and magnetism in a vacuum. So in space, devoid of material. As soon as you put magnetic fields and electric fields in materials, like glass or water or air, the constants change. So you get mu's and epsilons for that particular material. It can get really burdensome and confusing very quickly to have to keep track of all these permittivities and permeabilities and how the electric and magnetic fields interact. Well, ideally, we'd want to step away from sort of all of that deep electric and magnetic field stuff and be able to capture the idea of what's happening with light in a single idea. And that's exactly what we've done in optics. We have adopted something called the index of refraction. And you're seeing it listed here on this diagram. These n's right here, n1, n2, that number n, called the index of refraction, is a ratio between the speed of light in a vacuum to the speed of light in a material. It is a number. Let's just look at this for a second, okay? What is the index of refraction of outer space? How fast does light go in a vacuum? It goes c, right? That constant c is 3 times 10 to the 8 meters per second, right? And so what happens if you take c and divide it by c? You get 1. So an index of refraction of 1, n equals 1, is the lowest value you can get for an index of refraction anywhere. For any other medium, the index of refraction is higher. And so, for example, as we can see in the diagram here, the index of refraction of water is 1.333. Okay? Well, what does that mean, right? It means, if we take this index of refraction definition right here for water, right, then we'd see that the speed in water is going to be equal to the speed of light divided by 1.333. Well, 1.333 is that 4/3? Right? It's 1 and a third, isn't it? Right? So that's 4/3, right? So that's c over 4/3, which means it's 3/4 c. How fast is light going when it gets into water? 3/4 of the speed of light. Okay? Light slows down in any other medium. The fastest light can go is in the vacuum of space. Light traveling in any other medium does slow down, and the amount that it slows down is captured by this definition of the index of refraction. So if you have an index of refraction of 2, can you tell me how fast light's going in that material? Half the speed of light. Okay? So the bigger the number, the slower light gets. Okay? And these indices of refraction can be looked up for most materials, like water's 1.33, glass, most glass, like window glass is 1.52. That varies a little bit depending on the kind of glass it is. Diamond, I think, is 2.4 or something like that. We'll get as to why that number is important in a second. But you go and look these up. And a lot of my graduate work was spent figuring out what these indexes of refractions were for materials at very specific frequencies and wavelengths of light that nobody had ever studied before. Because knowing what light does when it interacts with the material is very important, and one of the keys to understanding how that works is to figure out what the indices of refraction are. Okay, so index of refraction, and what are the units? Sorry, of index of refraction? What are the units for the speed of light? Meters per second. What is the speed for any velocity? Meters per second. So what are the units of the index of refraction? No units. So meter per second divided by meter per second, that is no units. Okay? So it's just a number. All right. The governing equation for what all of these rays are doing is called Snell's law. It is not Smell's law with an M. It's Snell's law with an N. You got to wonder if he had any trouble in grade school. Into sine theta 2. It is a relationship between the different indices of refraction that light is encountering and the angles that happen. Okay? You'll see in this diagram I've adopted theta 1 and theta 2. Okay? This is what your book does. So, we have two materials. There's always a medium change when it comes to refraction. If there's no change in the medium, refraction is not going to happen at all. Okay? And then there's some sort of angle of incidence measured from where? Where do we always measure angles in optics? From the normal, from the straight up and down, right? Okay? So light's coming in at some angle. It bounces at exactly the same angle. That's the law of reflection. As the light enters the material, it changes its direction because its speed changed. And our refracted angle is going to be the theta 2 right here. So we have angle of incidence, and then we have angle of refraction. Notice, we are going in this first diagram from a lower index of refraction to a higher index of refraction. Whenever that happens, the angle gets smaller. That's predicted by this relationship up here. Mostly we'll just sort of brute force and plug and chug this equation, but if you really take a look at it, you'll see any change from low to high means the refracted angle is going to be bent closer to the normal. The angle is going to get smaller, and you're going to get closer to the normal. The reverse is true if your incident ray is traveling in a high index material and the light is transitioning to a low index material. So from higher to lower index, this ray gets bigger. It bends away from the normal. I'm going to do an example of this mathematically here in a bit, but let's talk about the consequences of index of refraction and why changes in index of refraction are so important to our ability to basically see anything.
When we look at a transparent object such as this glass eyedropper, we can see it even though it is perfectly clear. Differences in the refraction indexes of the glass and air allow us to see the edges of the glass. When we put the eyedropper in a liquid that has the same index of refraction as the glass and fill the dropper with the liquid, the eyedropper nearly disappears.
Okay. Snell's law tells us why we can see invisible things. It also is going to help us understand how our eyeballs work, how to correct problems with vision, and basically why pencils get bent when you stick them in water. Can I borrow your water bottle? I promise to give it up. And I won't take it. Okay, right? What color is the water? Trick question, has no color, right? What color is the plastic? Also no color, right? So how is it that you can tell that both of them are there? There's some reflections going on, right? You can see the reflections of the lights in here, right? Okay. But there's also refraction. Your brain is seeing the light bent and twisted. And so it is saying, well, light usually travels in straight lines, so if it's not traveling in a straight line, there must be something there. Why is it that the dropper disappeared? Did you catch what the liquid and the glass had in common? The same index of refraction. And so with the same index of refraction between the liquid and the glass, there was no bending of the light. And so our brains went, well, if the light's not being bent, there's nothing there. I'm not going to ask for a show of hands. You can just sit silently and answer this question to yourself. But how many of us have ever run into a sliding glass door knowing that it was open when in fact it was closed? This usually happens at a party and you're carrying a tray of food or drinks, right? Okay? But and you might think that you just weren't paying attention or something. You were tricked, okay, by your brain. Because how does your brain know that the sliding glass door is closed and the glass pane is there? The handprints, right? Okay. Anybody with pets or kids, right, knows that there's just smears all over the glass, right? So prior to the party, somebody probably thought, I better look like I know what I'm doing and clean my house, right? And cleaned the glass. Okay. So now there's no smudges on the glass, nothing to indicate, right, that it's there. You were probably in a low light situation of some, either a very bright light situation or a rather low light situation. And you were probably coming straight at the door, not at an angle, but straight onto the door. With no reflection cue from the dark inside of the house to the bright outside, and with no refraction cue, because you're hitting it at a 0 degree angle, okay? Your brain simply said, door open, okay? And then your nose discovered how close that thing could be. Just know that, again, when you have normal incidents, when the light comes straight down, what's the angle here? It's 0 degrees. And the angles in Snell's law, okay? The angles in Snell's law involve sine functions. What's the sine of 0? Got 50% chance.
1.
It's 0. Darn it. Okay, right? So there's zeros everywhere in Snell's law when you have a 0 degree angle, a normal incident ray. Which means there's no refraction of any kind that's taking place, which is why when you're looking at the fish in the water and it's directly straight down, you see the fish exactly where it is. The problem is that there's no ability to judge depth when you're looking straight down at something like that. But if you're looking at the fish from an angle, the fish is not going to be where you see it. And we'll draw that picture in a minute. All right, so let's do an example of using Snell's law to help us figure out some things. A lot of these examples are contrived, I guess is the word. Again, there seems to be this desire for physicists to make problems harder than they really need to be. But we will roll with it because that's how it is. Let me adjust the display here real quick so you can see all of that thing. All right, that should work now. There we go, now we can see all the text. Okay, so what the heck is going on here? An opaque cylindrical tank. What does the word opaque mean?
Not see-through.
Yeah, not see-through. Solid. Cylindrical cylinder. Okay, so I got a tank and it's a cylinder. Well, I know what cylinders look like. Am I able to draw them? No. Let's see here. So Okay, right? Diameter of 3 meters, so we know that this distance is 3 meters. It's completely filled with water, not drawn. When the afternoon sun reaches an angle 28 degrees above the horizon, sunlight, okay, so we're casting a shadow, right? And what they're trying to tell us is sunlight is coming in and striking one, also, don't draw all of these, I'm going to draw them and erase them, right? Sunlight is coming in and hitting the tank, right, okay? And a shadow is being cast. And the shadow is such that, okay, they want sunlight to cease illuminating any part of the bottom of the tank. In other words, again, don't draw. This part is all in shade, right? If sunlight's coming in, it's coming, right? And then all of this over here is illuminated, but any part I did there in orange would be in shadow, okay? And they've told us that the angle at which that happens is 28 degrees above the horizontal. So what's the first thing they're trying to trick you with here? That angle is not the angle we're going to be using, is it? Okay? Because all the angles in optics need to be measured from what? The vertical. So what's 90 minus 28? 62? Is that right? I should use a calculator for things like this. So I'm going to draw right here, and I'm going to say, okay, that's a 62-degree angle. You know what? I forgot to erase my orange over here. This is going to get in the way. There we go. So this comes down. Sunlight's refracting right there. And this is a 62-degree angle because this one's a 28-degree angle. Okay, so we established that. We have an angle, we'll call it theta 2 down here. That's the refracted angle. And the sunlight is going from air to water. The index of refraction of air, by the way, we cheat on this one. The index of refraction of air is also 1. Air actually has an index of 1.00, I never remember how many zeros, I think it's 3 zeros, 1.0001 to something, but it's really, it's basically 1. Okay, so we often cheat in optics a lot and just say the index of air is 1, even though we know that's the index of a vacuum and it's slightly different. Close enough, okay? Especially when you consider the indices of other materials that are like 1.33 and all that kind of stuff. Now we're less than 1/100% difference. Okay, so we know the indices of refraction of the materials, which means we know what the angle is going to do, right? As the sunlight enters the water, which way is it going to bend? Is it going to bend closer to the vertical or move further away from the vertical? Closer. A lower to higher transition means that our angle should be less, right? We're coming in at 62, and it should be less than that when we go to calculate it. The problem wants us to find, was it the depth of the tank? Yeah, how deep is the tank? And we're going to use some geometry to help us get that. But first, we need to get this angle. So we're going to employ Snell's law. Okay, there's Snell's law, the relationship. This is the relationship that dictates refraction. Okay, we are solving for theta 2. We want the refracted angle. So let's see here. Divide by n2, like that. And then we need to take the inverse sine. So it's the inverse sine of n1 over n2 times the sine of theta 1. Alright, so it's the inverse sine of first material, air, divided by second material, 1.33, times the sine of 62 degrees. So the sine of 62 is a number, okay? But notice, it's this ratio of indices of refraction that matters. And whenever you go from low to high, you always get a number smaller than 1, which is going to make the angle that we're finding smaller. When you go the other direction, and you have high to low, this ratio is always bigger than 1, which is going to make a bigger angle. Anyway, so we plug in numbers, inverse, we already plugged in numbers, and we get, where is it? 32 degrees. No, because that would be a 45-degree angle. Where's my example problem? It's gone. Yep, I don't have it on this page. What did I do with it? Do you hate it when your notes go missing? Anybody get it yet? I got 42 degrees. Anybody else get 42? 42 degrees. Okay, what does that mean? That means that this angle right here is 42 degrees. They want us to find out how deep the tank is. So this has nothing to do with optics now. The optics part is done. I found my angle according to Snell's law. Now I have a triangle with a 42-degree angle in it up there, and I know that that side is 3. And I want to find the height side over here. What are we going to do? Can't use cosine because cosine would involve the hypotenuse. We don't know the hypotenuse. If you don't know how if you don't have a hypotenuse, what's your only resort? Tangent. Tangent of the angle is going to be the y over the x, so tangent of 42 is going to be 3 over the height. So the height is going to be 3 divided by the tangent of 42. Tangent 3, and I got 3.33. Anybody else get that? Nobody else tried? Nobody else cares. That's good. It's just numbers. Okay. So there's the depth of the tank. I give this example to you again to show you, number 1, make sure your angles are measured from the vertical, right? Number 2, that they're contriving situations where, why can't they just ask me to do Snell's law, right? Okay, and then there's all this other stuff that they want you to do, right? Probably some trig, some geometry somewhere, something like that, right? Because your life is not complicated enough. All right, so let's investigate one of the consequences of Snell's law. Those are N's, by the way, not H's. Okay, so what we did last example was we went from in air to water. But this time, let's go from water. We'll send in a beam coming up like this. We'll call this our angle of incidence. And so we're at 1.33, and then we got 1 up there. So we know that it's going to be, what's the angle going to do if we go from higher to lower? It's going to be away. It's going to get bigger, right? Okay. So we know that the angle is going to do something like that, right? If I take this angle, the incident angle right here, okay, and I start increasing it, the refracted ray is always going to have a bigger angle, isn't it? So as I increase theta 1, if I take it from 0 to 90, before I ever get to 90 degrees, the refracted angle is going to hit 90 degrees first. It's ahead, right? It's always a bigger angle, and so it's going to get to a point where the refracted angle is 90 degrees. So to ask the question, right, what angle of incidence, theta 1, do I need for theta 2 to be 90 degrees? I can say, well, I know what N1 is. I'm going to call it the critical angle right now for reasons that will be apparent in a second. And I know N2, and I know the sine of 90 degrees. What's the sine of 90 degrees? 1. Not 0 this time. Okay? Sine of 90 degrees is 1, which means that my critical angle will be N2 over N1, and I can find this critical angle by taking the inverse sine of the ratio of the indices of refraction. I don't know about you, but I get confused really quickly over what's 1 and what's 2. And so let me give you a trick that I've adopted in my optics career that has guaranteed that I never get this wrong, okay? And this trick is based on the physics of what's going on here. Because this critical angle can only happen if light is going from a higher index to a lower index material. It cannot happen the other way around. If we were going the opposite direction, the angles are less. And so you can get to 90 before you get to 90 on the other side. This only happens when you're trying to get light to go from higher index to lower index. So, while your book might write the critical angle like that, I always write the critical angle as the inverse sine of the lower index material divided by the higher index material. How do I know this works? The inverse sine function is saying, okay, I want my calculator to tell me what angle would I need to put into a sine function to get a number. Now the sine and cosine can never be bigger than what? Of any angle, any value you put into the sine or cosine, what will you always be less than or equal to? Oh, come on, you know this. What's the most that cosine can ever be? What's the cosine of 0? It's 1. What's the cosine of 90? 0. And what's the cosine of anything between 0 and 90 degrees? A number between 0 and 1, right? And then on the other side, you can go from 90 to the other side to 180, and you go from 0 to -1, right? And then you start flipping back around. So cosine and sine functions can never give values bigger than 1. Okay? So we're asking the sine function, what ratio gives us a certain angle? And if we try to ask the sine function, what angle gives us a value of the sine for a number bigger than 1, what is your calculator going to tell you? Error, right? And so what I don't want you to do is sitting there going, what? Error? What does that mean? Right? Okay? Because it can get confusing over what's 2 and what's 1 and all that kind of stuff when they write it like this. But if you write it like this is the critical angle on which total internal reflection happens. If you always take your low index and divide by your high index, you're always going to be guaranteed a number less than 1. And so you're going to get an answer.
But only in this instance.
But only when light is going from high to low. Again, total internal reflection does not happen from low to high. It just doesn't. Now, why do I keep calling it total internal reflection? When you achieve a refracted angle of 90 degrees. So there's certain angles, okay, of incidence where the light will be refracted out, and as we increase this angle, this gets closer and closer to the surface. At the critical angle, the light is refracted at 90 degrees, meaning that the light does not exit the material. It is totally internally reflected. within the incident material. And any angle bigger than the critical angle means that there will only be reflection. There will be no transmission. This isn't like no transmission, like, perfect physics world. This is like there is no transmission because the light can't refract out of the medium. The angle at which total internal reflection takes place is called the critical angle, and I just showed you how to calculate it. So let me show you some examples of what total internal reflection looks like, and then why it's important to you and getting all your TikToks and Instagrams.
We'll use this water tank and a parallel beam of light to demonstrate total internal reflection. A chemical in the water fluoresces when the light strikes it, showing the path of the beam. This mirror reflects the beam up to the surface of the water at any angle we choose. When the beam strikes the surface straight on, very little of the light is reflected. At a shallower angle, more of the light is reflected, but most still passes out into the air, as shown by this thread screen. Notice the misalignment between the beam in water and the beam in air. At a still shallower angle, the beam is refracted so much that it becomes parallel to the surface.
That's not a parallel line.
This is known as the critical angle situation. If the beam hits the surface at an angle shallower than the critical angle, all the light is reflected back at the surface, and none crosses through. This is known as total internal reflection.
It doesn't get out. Do you notice how when the angles were like really close to the vertical, the light was able to get out? But then there was this moment, right, where it just stopped getting out of the water and it was totally reflected inside of the water? From below, this is what that phenomenon looks like. I used to swim in high school. You go down to the bottom end of the pool, you dive down, you see all the lane lines and stuff like that. What you would see is a reflection of the bottom of the pool above you, but then there would be this circle, okay, where you could see out. You could see the ceiling, you could see the sky, you could see whatever's out there. The lifeguard trying to rescue you, whatever's happening, right, okay? But at certain angles, which in water is 49 degrees, 41.2 degrees, okay? So this means if you're standing and looking straight up, your angle of incidence is 0. If you go 42 degrees to one side and 42 degrees to the other for a total of 84 degrees, okay, your field of view is 84 degrees. Everything past that is going to be a reflection of what's underneath the water, okay? If you're scuba diving, this is what the sky looks like, okay? Everything underneath is a reflection of what's going on underneath the ocean, and then there's just this ring of skylight, okay, that you can see. And I didn't take this picture, but this scuba diving buddy is getting in the way. Let's show you this.
These acrylic tubes will be used to show the type of total internal reflection which makes fiber optics communications possible. When a laser beam is aimed into the end of this tube, the beam bounces off the walls and is guided along the length of the tube, emerging from the far end. The laser beam can also be guided along this curved tube. Real fiber optics cables can bend around corners without losing any of the light passing along them.
So that light there is totally internal reflected inside of that acrylic. I have a twisty piece of acrylic here, okay, and I've got a green laser, right? I can point the end, okay, of my laser into this acrylic, and this end lights up pretty brightly, okay? Now, we're cheating a little bit here so that you can see the laser inside of the acrylic, okay? A real fiber optic would have no loss of light out the sides, because the angles would always be there, right, okay? But that beam, right, is pretty bright coming out the end of there, and it's not terribly bright coming out the sides. The laser light is literally trapped inside of a fiber optic because of total internal reflection. So that means we now know something about how fiber optics are made. what must the index of refraction of the glass be compared to the surrounding material? Total internal reflection only happens when? Higher to lower, right? So the glass has to have an index of refraction higher than any of the surrounding jacket, material, whatever they're coating the fiber optic in, right? Those all have to have indices of refraction that are lower than the glass that's there. Water has a higher
We now
index of refraction
demonstrate
than air.
total internal reflection of laser light in a water jet. A laser is aligned such that its light passes through a water tank and into a tube at the bottom of the tank. Powdered coffee cream has been added to the water to make the laser beam more visible. When the stopper is removed, water squirts out of the tank into the container below. The laser beam is reflected internally and follows the water jet into the tank.
It's totally in the
In
water.
this close-up view, we can see the internal reflections of the laser beam in the water jet.
Just like it's 100% in that water, and this is going to kind of fail as the water pressure gets lower, as it drains. Look at how the angle changes. You will suddenly see the drop-off in light when we finally exceed the critical angle. So it's still bouncing totally internally inside that water stream. And right there, did you see how it just kind of died? Right? Now that laser beam is getting out. Okay? So, I mean, don't go make your fiber optics out of water. Right? But just as a demonstration of what's going on. Okay, so why are fiber optics important? They're so important, and yet you have no idea where, why, or what they are, or what they're doing. Not to date myself, but you know I'm old already, so that's not a secret. When I would make phone calls from the Philippines back in the early 1990s, it started off, and we would call, and we'd have to have the telephone call routed through a satellite. There's about a 4-second delay between you saying hi and it would be 2 seconds for them to hear it, and then 2 seconds for them to right, okay, and all that kind of stuff. So it was this built-in delay, and so your telephone conversation very much was, "Hi, how you doing?" And then they would respond, and you'd end up talking over each other, right? Okay, and it was all kinds of fun. But halfway through my mission, the first telephone calls were being done over fiber optic cables across the Pacific Ocean. And I remember that first time we got routed through a fiber optic instead of a satellite, because it sounded like my family was there, like in the room with, because the satellite had it was like talking over a CB radio almost. There was interference and static and this delay and all this kind of stuff. But with the fiber optic one, light speed. Like how fast is light traveling in a fiber optic? As fast as light can go inside of acrylic. And so it was like they were standing right there. There was no more delay. It was crystal clear. I remember tearing up because it felt like they were so close and yet they were so far away. And it's kind of something we take for granted now, right? My wife and I are planning this trip to Great Britain. My wife's been calling a bunch of places in Great Britain. It's like Great Britain is in our living room, right? Like it's just instantaneous. You can talk all the time and all that kind of stuff. So fiber optics revolutionized voice communication, but they also revolutionized internet communications. My first internet was a 200 baud modem. Yeah, I think it was 200 baud, and it had a switch where I could go to 1200 baud, but only if the other modem could, I was connecting to could support it. This is literally when you had to dial up, okay, to get internet. You probably never experienced this. 200 baud means that I could get 200 bits of information every second, and one character is 200 bytes of information. One character is 800 bytes. Basically, my internet speed was 0. Okay? Forget streaming anything. You were lucky if you could get text to appear on the screen faster than you could read it. Normally I could read faster than the modem was able to download just text, right? Nowadays, I have gigabit service at my house, meaning that 1 billion bits per second can flow into my house, right? And just again, by way of contrast, to stream Netflix or anything else, and YouTube, anything like that, requires like 4 to 10 megabits per second, okay? For a deep, that wouldn't be 4K, that would be like 1080p, okay? All of this speed gain comes from something called bandwidth. And bandwidth is complicated, but we can simplify it into the amount of information that can be sent per time, okay, down a cable. Copper cables are bandwidth limited by the nature of the material that a copper cable is made out of. So Ethernet cables, all those kinds of things, there's a limit to the copper and its ability to send information. Fiber optics can send a lot more information per time because we're sending them on laser pulses, and we can jam a whole bunch of laser pulses into a fiber optic compared to the singular signals that can flow down copper wires. And so an analogy I like to use is if you imagine like the dial-up that I used to have being like, if the bandwidth, it can be represented by this pencil here, right? The thickness of the pencil, okay? Then nowadays, the connection I have at my house with my gigabit Ethernet would be a pencil that has a diameter that is bigger than this building, about the size of this building. We used to use a descriptor. We said, well, you know, Ethernet is like this, and a fiber optic is like a sewer pipe, like a 6-foot diameter sewer pipe. It's like house size now, right? Okay, like the analogy of the amount of information that can come down a fiber optic now is incredibly big compared to, say, what the Ethernet cables and things can do in your house, or Wi-Fi for that. Wi-Fi is like a pin compared to this. Okay, Wi-Fi stinks when it comes to bandwidth. Okay, it's getting better. There's a brand new specification for Wi-Fi, Wi-Fi 7. Don't go out and change your routers or anything. Do it in 4 years. But they just did the specification for Wi-Fi 7, and I think they said that they're going to support up to 10 gigabits per second over Wi-Fi, which is now approaching the limit of Ethernet. So it's coming into parity. But the nice thing about Wi-Fi, right, is that you don't have to have your phone plugged into the wall, right? Everywhere you go, you can just get it wirelessly. It's slower, but it certainly is more convenient. That's plenty enough for today, isn't it? Okay. Let's reconvene tomorrow. We'll pick up at chapter 26. We're going to cover a few more sort of extra topics, and then we're going to get into lenses. See you tomorrow.